the induced EMF is given by E is equal to minus L into di by dt, that is an expression for self-inductance which we are already familiar with. So the total voltage in a series LCR circuit is sum of the voltage across inductance plus voltage across capacitor plus voltage across resistor. That's my next equation. Square root of R square plus Xc minus XL, the whole square is analogous to resistance and we call Z as impedance. Hello everyone, welcome to session 3 of chapter 7 alternating current. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. In the last session, we have learnt about the introductory part of alternating current and we have also learnt about what if an voltage or an AC source is applied to a pure resistive circuit, pure inductive circuit and pure capacitive circuit. In today's session, let us learn about LCR circuit. So in this session, we are learning about an expression for impedance. So impedance is nothing but a term which is analogous to resistance, which is denoted by Z, and an expression for current and phase angle in series LCR circuit with the help of phasor diagrams. What is LCR circuit? It is in inductance, capacitance and resistive circuit. For that, I have considered a series LCR circuit. You can see here inductance, capacitance and resistance are connected in series. Now this graphical representation shows voltage is ahead of current in case of inductance and current is ahead of voltage in case of capacitance, and they are in phase with each other, which we have studied with the help of phasor diagram in our previous sessions. Now these three are connected in series and that is connected to an AC source. This is the circuit symbol of AC source where the AC voltage is supplying to the circuit. So we have considered a series LCR circuit connected to an AC source as shown in the figure. So as soon as an AC source is connected to the circuit or to the components, there exists an instantaneous voltage and it is given by V is equal to Vm sin omega t, which is my equation 1. And the EMF will induce in the circuit. The induced EMF is given by E is equal to minus L into di by dt, that is an expression for self-inductance which we are already familiar with. Now the voltage across the circuit, since there is a resistor, the voltage across the circuit is given by VR is equal to I into R according to Ohm's law. There is a capacitance also in the circuit. So the voltage across the capacitance is VC is equal to Q divided by C. We have considered these conditions separately in deriving those three expressions when the AC source is connected to an inductor, capacitor and resistor, which we have learnt in our previous session. Now there is an EMF, there is also a voltage. So it's a closed circuit. By applying Kirchhoff's voltage law, we get V is equal to L into di by dt, that is an EMF, plus I into R, that is voltage across resistor, plus Q divided by C, that's voltage across capacitor. This is the total voltage throughout the circuit. So this is our V. So I'll call this as equation 2. Now there exists an instantaneous current. And how can we write the equation for instantaneous current? We know the instantaneous current is given by I is equal to Im sin omega t plus phi, because there exists a phase difference between L and C. So the alternating current in each element is the same at any instant of time, having same amplitude and same phase, and hence we can write the current I is equal to Im sin omega t plus phi, where phi is the phase difference between the source voltage and current. So we know VR is parallel to I, that is the voltage and the current in case of pure resistive circuit are in phase with each other, and VC lags the current by pi by 2 in case of pure capacitive circuit, and VL leads the current by pi by 2 in case of pure inductive circuit. So the total voltage in the series LCR circuit is sum of the voltage across inductance plus voltage across capacitor plus voltage across resistor. That's my next equation. Now with the help of this we can write, we know VR and I are parallel to each other, they are overlapped, but VL and VC are opposite to each other because VL leads the current and VC lags the current. So combining all the three phasor diagrams which we have derived individually, we can represent it in the phasor diagram for series LCR circuit, where VL and VC are opposite to each other, and VR on which there is a line or there is a vector of current, which means current and voltage in case of pure resistive circuit are in phase with each other. So this is since the phasors are rotating in anti-clockwise direction, angular speed with respect to time plus the phase angle, and this is the phase difference between VL and VR. So considering only VL, VC and VR, we can represent this in this way. That figure 2 shows only the VL, VC and VR, how they are related to each other, what is the phase difference between VL, VC and VR. So this diagram shows us very clearly. So now to calculate the total voltage, or we know voltage across resistor, that is given by VR is equal to Im into R, that is peak current into resistance, and VC is equal to Im into Xc, where Xc is capacitive reactance which is analogous to resistance, and VL is equal to Im into XL, where XL is inductive reactance which is analogous to resistance again. So from the figure 2, we have a triangle OAE. So consider triangle OAE, it's a right angle triangle. So we can apply the Pythagoras theorem to arrive at the expression of impedance. So according to this, OE square is equal to OA square plus AE square by applying Pythagoras theorem. So we can write OE square is equal to OA square plus AE square. Now what is OE square according to the diagram? OE is nothing but Vm, that is peak voltage, and OA is VR, and AE is VC minus VL. So substituting all the terms in the above equation, we get Vm square is equal to VR square plus VC minus VL the whole square. What is VR but? It is Im into R. So substituting that, we get Im square into R square plus VC is nothing but Im into Xc. So it is Im into Xc minus Im into XL the whole square. Now Im square is common in all the terms, so taking it outside, so we get Im square into, we remain with R square plus Xc minus XL the whole square. So here in the LHS we have Vm. So we can represent this as Im square is equal to Vm divided by this whole term, that is R square plus Xc minus XL the whole square. So taking square root for this equation, we get Im is equal to Vm, because we have Vm square here. So Im is equal to root of Vm square, square and square root will get cancelled. It is Vm divided by root of R square plus Xc minus XL the whole square, or we can write it as Im is equal to Vm divided by Z. This whole term is replaced by a term called Z, which is nothing but the impedance, where Z is equal to square root of R square plus Xc minus XL the whole square is analogous to resistance, and we call Z as impedance. Now we have calculated, or we have derived the expression for current, voltage and impedance. Now let us write the expression for the phase angle. Phase angle is denoted by phi. If phi is the phase angle between current and voltage, then from triangle OAE, this phi, which is equal to tan inverse of, or tan phi we can define first. Tan phi is equal to VC minus VL divided by R. So look at this triangle, VC minus VL divided by R. What is tan theta? So tan theta is equal to opposite divided by adjacent. Now opposite is VC minus VL and the adjacent is VR. So tan theta we will get it as VC minus VL divided by VR. What is VC? It is Im into Xc. VL is Im into XL and VR is Im into R, where Im is common in the numerator, so we can write it as Im into Xc minus XL divided by Im into R. Cancelling Im and Im, we get Xc minus XL divided by R. But phase angle is denoted by phi, so phi will be equal to tan inverse of Xc minus XL divided by R. This formula can also be written as XL minus Xc divided by R if the inductive reactance is greater than the capacitive reactance according to the condition. This is very useful in numericals. So keep these 2 points in mind, that is if Xc is greater than XL, Phi is positive and the circuit is predominantly capacitive. So the current in the circuit leads the source voltage, because we know in case of pure capacitive circuit, when an AC voltage is applied, current always leads the voltage. So if XC is less than XL or XL is greater than XC, then phi value, the phase angle, is negative and the circuit is predominantly inductive, where the current in the circuit lacks the source voltage, because we know in case of inductive circuit, voltage leads the current by 90 degree. So let us learn the definition, or what is inductive reactance and capacitive reactance briefly. So inductive reactance is denoted by XL, which is nothing but the opposition to the AC offered by purely inductive circuits, and it is called as inductive reactance. It is analogous to resistance. It is given by XL, which is nothing but omega into L. This can also be written as 2 pi nu into L, because omega is 2 pi nu or 2 pi F. The SI unit of inductive reactance is ohm, which is denoted by this symbol, because it is analogous to resistance. The next one is capacitive reactance, which is denoted by XC. It is again nothing but the opposition to the AC offered by a pure capacitive circuit. It is called as capacitive reactance, which is again analogous to resistance, and it is given by the expression XC is equal to 1 by omega C. So XC is equal to 1 divided by omega C. It can also be written as 2 pi nu into C, because omega is equal to 2 pi nu, or you can also write it as 2 pi F into C. The SI unit is again ohm. So what is impedance then? It is denoted by Z. It is nothing but in a series LCR circuit, the opposition offered by circuit to the flow of AC current, and it is denoted by a letter Z. It is again defined as the ratio of RMS value of voltage to the RMS value of current. So generally Z is equal to VRMS divided by IRMS. There is another formula for Z which we have derived, that is Z is equal to square root of R square plus XC minus XL the whole square. So this is about the expression for impedance, phase angle, current and voltage in a series LCR circuit. We have even learnt about the capacitive reactance and inductive reactance, which are very important examination point of view. In the next session, we'll learn some more interesting concepts. See you all in the next session. Until then, keep learning all of you. Thank you.